for joining us this morning. Welcome to this morning's session, which features Dr. Gregory Dipple updating and presenting initial results from the carbon mineralization potential assessment for BC project. So this is looking at the potential for ultramafic rocks in BC to sequester carbon dioxide. The part of this research that's funded by Geoscience BC is just one part of a much wider program of research being led by Dr. Dipple and his colleagues. And the initial report is available now, literally in the last couple of minutes, on the Geoscience BC website. You should also have received an email in the last few minutes with a copy of the report. And also, if you go to the geosciencebc.com, you just go to the homepage, you'll see this project is featured on the homepage, and you can find the reports on the project page. My name is Richard Truman. I'm the Director of External Relations at Geoscience BC and your MC for today. I'm joining you from the traditional territories of the Musqueam, the Squamish and the Tsleil-Waututh Nations. Joining us here today are Krista Pellet, Vice President of Minerals at Geoscience BC, and she'll provide a brief introduction to Geoscience BC. I'm also pleased that we're joined by Dr. Sean Barker as well, the new director at UBC's Mineral Deposit Research Unit, or MDRU, as many of you may know it. I think he's on day 2 of a new job, so we're pleased to be able to welcome him for the first time. And of course, Dr. Gregory Dipple, who will talk you through some of the initial results from the project. In the background as well, we also have Geoscience BC's Candice Appleby looking after some of the technology and keeping things running smoothly today. A couple of housekeeping notes before I hand you over to Krista. We should have plenty of time for questions today, so please use the Q&A feature at the bottom of your screen during or after the talk, and we'll answer as many questions as we can. And secondly, this session is being recorded, so that means that it will be available to view on Geoscience BC's website and Geoscience BC's YouTube channel in the coming days, along with a PDF of the presentation as well. So that's it from me. I will hand you over to Krista, and you'll see me again at the end of the session for the question period. Over to you, Krista.
Thanks, Rich. So my name's Krista Pellet. I am the Vice President of Minerals at Geoscience BC, and I'm speaking to you today from Kamloops in the traditional territory of the Tk'emlúps to Secwepemc First Nations. Thank you for joining us this morning. Most of you are probably quite familiar with Geoscience BC, but for those who aren't, Geoscience BC generates independent, relevant public earth science research and data about BC's mineral, energy, and water resources. Our research advances knowledge of BC geology, informs responsible resource development, and encourages investment and stimulates innovation in the province. Geoscience BC has been around since 2005 and complements the existing government agencies and scientists such as the BC Geological Survey, as well as the BC Oil and Gas Commission with their energy and water research projects. Geoscience BC's collaboration with the resource sectors, academia, communities, Indigenous groups, and government helps to develop and share unbiased and credible earth science research and data. For every $1 Geoscience BC spends on minerals research in BC, $6.60 is invested back in mineral exploration in the province. To date, we've 156 completed and current minerals projects in BC, and all of our results and data are public and available on our website. We have partnered with UBC's Mineral Deposit Research Unit, BRIM, and the new Carbon Lab that are advancing science and innovation in BC. And today we're going to hear from Dr. Greg Dipple about the initial peer-reviewed report from the Carbon Mineralization Potential Assessment for BC project. This preliminary report, as Rich just mentioned, is now available on our website, and a final report and data will come out in the new year. Geoscience BC and UBC have a strong history of working together on minerals projects, so I'm pleased to pass you over to the incoming director of MDRU, Dr. Sean Barker, before we hear from Greg. Sean, welcome to your new role, and over to you.
Thanks very much, Krista. Good morning, everyone. I just wanted to thank you all for connecting with us. As Krista said, my name is Sean Barker. I'm the new director of the Mineral Deposit Research Unit, and as Richard mentioned, it is day 2 or day 1.2 now. So as the director, I'm really pleased to be able to say a few words about this project. A little bit of history. This project began as an MDRU project back in 2001 when Greg Dipple first carried out fieldwork at Atlan for a master's of Science research thesis carried out by Lyle Hansen and collected samples. I actually worked on a little bit on this project myself as part of my postdoc in MDAU in the late 2000s, where I worked with Greg, Sasha Wilson and other students on helping to develop new methods to enable us to fingerprint and quantify the amount of atmospheric carbon that was being captured within mine tailings. Now in 2020, this project's been running for almost 20 years, and its various components cover many of the strengths for which MDAU is well known. The project started with field and laboratory studies of materials from abandoned and active mines to identify the volume of carbonate minerals found within mine tailings and to identify the source of that carbon. Was it coming from the atmosphere or was it bedrock? More recently, the research has moved from documenting atmospheric carbon uptake and moved into implementation of pilot scale trials in active mine sites to assess the workflows and strategies needed for accelerating carbon sequestration. The work that you'll see today, and indeed throughout the broader CO2 project, captures many of the themes that are embedded in both MDAU and the Bradshaw Research Initiative for Minerals and Mining, or BRIM. This includes taking our fundamental geological and geochemical knowledge and then working collaboratively with researchers from many areas, including geophysics. And today you'll see some of the results from working with the Geophysical Inversion Facility at UBC, as well as much more broadly working with microbiologists, mineral processing experts and economists to look at the feasibility of carbon sequestration within mine tailings. In the presentation today, you're going to see some of the aspects of that collaboration. And as the MDAU director, I look forward to seeing many more results from both this project and creating future projects with similar degrees of collaboration and innovation from MDAU and BRIM researchers, and working more broadly with the geoscience community throughout British Columbia and Canada. So thanks very much, and I'll pass you back to over, I believe, to Greg. So thanks, everyone.
Hello, thank you, Sean and Krista, for the introduction, and welcome everyone today for a delivery of a preliminary report on the carbon mineralization potential for ultramafic rocks in BC. As Sean mentioned, this has been a project that's in its 20th year and really advanced significantly in the last few years. And today we'll provide an overview of one aspect of the project that looks to essentially prospect for highly reactive rocks, which can be used to capture and sequester CO2 from the atmosphere with the goal of reducing or eliminating the greenhouse gas emissions associated with mining. So I believe you should be able to see my slide deck now. So this project is funded by Geoscience BC. It represents a collaboration between the Mineral Deposit Research Unit, the Bradshaw Research Initiative for Minerals and Mining, and the BC Geological Survey. The authors are listed here. Particularly, you want to point out the important contributions from both geologists, geochemists, and geophysicists, ranging from undergraduate students up to senior faculty members. The authors of the report are Diane Mitchison, Jamie Cutts, Dom Fournier, Annika Naylor, myself, Craig Hart, Connor Turvey, Mana Rahimi, and Dejan Milodragovic. And this project is funded by Geoscience BC. The report, as mentioned, is available for download now, and I will just spend the next 20 to 25 minutes highlighting some key parts on that report, and put on the upper right here a link to the larger website associated with the Carbon Mineralization Lab out at UBC. This project fits within a larger carbon dioxide sequestration project that's headed by UBC. It has three components. The largest component is looks at sequestration of CO2 in ultramafic mine tailings. And that right now is currently in field pilot stage at a number of sites, in particular looking at both flue gas capture of CO2 and mineralization at the Gaucho Quay Diamond Mine from De Beers in the Northwest Territories last year. And this year we ran a direct air capture field pilot using tailings from test work from the Baptiste deposit in North Central BC. That's an FPX property. This is the first project within carbon mineralization potential. So today we're reporting on the potential for British Columbia, and we look forward to advancing this approach to other localities and other jurisdictions. Essentially what we're doing here is taking our understanding of the mineralogical and the geological control on the potential to capture and store CO2 and put our explorationist hats on and try and prospect for the most reactive rocks. And lastly, there's a third area where we use analogs to understand the processes that are important for carbon capture and storage. And we also use natural analogs to test and to understand and to demonstrate the long-term storage of CO2. And this project as a whole represents funding from a number of sources and a number of collaborations from universities around the world. What's behind this project overall is the idea that ultramafic rocks form out of equilibrium with the hydrosphere and the atmosphere, and when they get exposed or brought to the near surface, they are highly reactive to carbon dioxide. That process creates or stores carbon in mineral form, and in the graph on the upper right from a plot from Klaus Lackner's paper in Science, we can see that storing carbon in mineral carbonates is really the holy grail of carbon sequestration. It has a storage time of, it's counted in over geologic time, so it's permanently stable, and the capacity is significant. In fact, roughly 90% of carbon on Earth is currently held in minerals, reflecting this thermodynamic stability. So we want to take advantage of that. The problem is that that process normally happens very slowly. The process is one in which we strip metals or cations from tailings, such as magnesium from ultramafic tailings. We couple that with carbon dioxide that comes either from a point source, such as electricity generation, or from air, and we precipitate magnesium carbonate minerals, which represent this dense permanent CO2 storage capacity. We know that this process happens at a significant pace in some environments, and we want our goal here is to understand what limits the rate of these processes and accelerate it. So our past work in this area has demonstrated, for example, that at the Mount Keith nickel mine in Western Australia, their tailings facility captures CO2 from the atmosphere and stores it in mineral form at a rate of 40,000 tons per year of CO2. That represents an 11% offset of total mine emissions. And that's mineralization of CO2 and capture from the atmosphere that was happening both unintentionally and unknowingly. And we know that through the application of tailings treatments and other approaches and new ways of storing tailings, that we can take that rate and increase it significantly. And we've been at the forefront of putting out new technologies, such as taking technologies from soil science in order to measure the rate by which CO2 can be captured in these systems. I'm going to show a short video here to emphasize this. The point of this video is to emphasize that this process is real and that it can happen rapidly when we have the right material. This is a tailing sample from the Gaucho Quay diamond mine in the Northwest Territories, and it's been a bit of room air has been isolated against the tailings with a CO2 sensor. The kink in the green line here represents the time at which the air was isolated against the tailings, and this video is sped up about 8-fold. But we can see that the room started with about 700 parts per million CO2, and in the time scale of the first 3 minutes, we've removed about 150 parts per million of that 700. And it continues to go, and the CO2 content continues to decline, and we can see that over the course of about 6 minutes, we've removed roughly half of the CO2 that was contained within that gas, within the room air that was isolated up against the mine tailings. So that's really meant to emphasize that this process can be rapid and it can be significant, and that's why it represents an opportunity to capture and store CO2 from the atmosphere using a waste stream, in particular mine tailings. But the capacity to do that is highly variable, and in many instances is not very large. So it's really important to understand which rocks and which minerals are host of the magnesium that can be released very rapidly to allow for this rapid capture of CO2 from air. And so for that, we've developed techniques to measure the labile fraction of the magnesium in tailings. This shows essentially the reaction rate by which we release the magnesium from the minerals in the tailings as a function of the total amount of magnesium in the sample. And we typically get two classes of magnesium. We get a fraction that's released very quickly, and then we get the residual magnesium that's released at much slower rates. And these slower rates are what we would normally expect from sort of textbook mineral dissolution kinetics studies. But we find that there are trace minerals and there are surface processes on sheet silicates and clay minerals that can be an important source of magnesium that make it possible to capture and store carbon quickly, and that equates to inexpensive carbon sequestration in line with roughly the value of the carbon tax today in British Columbia. So a really important understanding is to realize that this labile fraction here this is again reaction rate versus labile fraction. It's controlled fundamentally by the mineralogy of the tailings, and we can see a large variation within different tailing samples. If we want to capture CO2 from air at time scales that are relevant for mine operations, we really only access this labile magnesium, and we leave the non-labile magnesium behind. If we can identify those materials that have high fractions of labile magnesium, we can achieve significant rates of carbon capture and storage. So this project actually builds on, as Sean mentioned, the very first project that I worked on in carbon sequestration, Lyle Hansen's master's thesis that started in 2001. The main results of it were published in 2005 in Canadian Mineralogist. And in this, we actually used magnetic susceptibility, 1,600 measurements of magnetic susceptibility across an outcrop of partially carbonated ophiolitic rocks to show that the variation in magnetic susceptibility correlated with changes in mineral content. And ultimately, we even used this to track the progress or the amount of carbonation reaction. And this plot here shows a prediction of the whole rock CO2 content based on the magnetic susceptibility values across two reaction fronts around a central vein system compared against the actual measured values. So we can see that we could actually, as a first approximation, we can use geophysical properties to understand changes in mineralogy when we're in this situation where we're carbonating ultramafic rocks. And that's really the premise behind this entire project. Can we take the known occurrences of ultramafic rocks throughout British Columbia and use existing publicly available geophysical data to prospect for those bodies that are going to be highly reactive to CO2? And it's really based on two types of reactions. This plot here shows the loss on ignition, or the volatile content of rocks, as a function of their mineral content. And we start off with fresh igneous ultramafic rocks. They're virtually volatile free. Typically, these rocks are hydrated or serpentinized, and then those serpentinized rocks are susceptible to carbonate alteration. And so as we progress from left to right through a series of reactions that add water to the rock and then add CO2 to the rock, we see an increase in serpentine and trace minerals, which are important for CO2 reactivity, but then those minerals are destroyed by carbonate alteration. So we want to be able to identify these rocks, the serpentinized rocks, and distinguish them both from the fresh igneous rocks and also distinguish them from the carbonate altered rocks in order to identify the rocks that have the best potential to capture CO2. So for this project, we have built a physical properties model. Jamie Cutts did incredible work on this area. So this table shows the database that we're using to build this physical properties model. These come predominantly from British Columbia, a total of 647 samples, of which roughly 600 have had geophysical properties measured at UBC, and about 100 some have been validated with more rigorous instrumentation at the Geological Survey of Canada. And that's been supplemented by quantitative X-ray diffraction mineralogical data on 265 samples. So these come from both ophiolitic ultramafic rocks as well as intrusive ultramafic rocks. And this map on the left, the inset shows the study area for this project. We really span BC from the southernmost to the northernmost boundaries. And the black dots in here show where the main ultramafic occurrences are. So our job here is to take this map of ultramafic occurrences and overlay it with the geophysics to try and understand where the best rocks are to be used, that could be used for capturing and storing CO2. So basically we're taking existing 200-meter gridded aeromagnetic data from Natural Resources Canada and overlaying that with the bedrock geology map of British Columbia. So again, the data that really underlies this project is information that's already publicly available. It's been augmented with these physical properties models and some new approaches for geophysical inversions in order to identify and image these highly reactive rock bodies. When we overlay the geophysics on the geology, we came up with a classification scheme by which to look at all the various polygons or occurrences of ultramafic rocks. And in a nutshell, classifications A, B, and C represent ultramafic rock bodies where there's a strong correlation with magnetic highs and mapped rock bodies that give us confidence that these are significant sized bodies of ultramafic rocks that contain a large amount of serpentinized rock that has not been carbonate altered. Then there's a number of other polygons in which the geophysical response suggests that these rocks are either relatively unserpentinized or uncarbonate altered, or rocks that are generally too small. So we're essentially distinguishing between classifications A, B, and C, which represent areas that have high potential for carbon sequestration, carbon mineralization, whereas the other classified localities do not. So if we apply this across British Columbia, so this again shows the existing ultramafic rock bodies in BC now classified where classes A, B, and C are shown in red, and classes D, E, F, and X are shown in black. And we can see then we start to outline which of these bodies have significant amount of serpentinization without significant carbonate alteration, suggesting that they would represent good rock bodies to look at for carbon sequestration potential. These A, B, and C polygons or occurrences represent roughly 46% of the known ultramafic rock bodies in British Columbia, but in terms of their aerial extent, they represent 75% of the known aerial extent. So they're really focusing on roughly half the mapped ultramafic rock bodies, but they tend to be the larger ones where we're generating significant volumes of magnetic response representing significant amounts of serpentinized material. And we would argue that those are the areas that should be priorities for looking at potentially building carbon sequestration projects. Now we could take these data, and we know the aerial extent of those bodies, and make some very simplistic geometric assumptions about the amount of material that's present of serpentinized rock. But we've chosen to use geophysical inversions to try and image these bodies at depth. So this shows an example from the Descartes area in north central British Columbia, where we can look at the geophysical response and 3 different geophysical inversions that use a different set of normalizations or LP normalizations, which is basically tell the model whether we're looking for very tight, sharp bounded bodies or looking for bodies that have more smooth boundaries and are more diffuse. And we can look at how the range of magnetic susceptibilities vary across each of those different models. So we do multiple inversions for each site, and we can then look at their geometry, their shape, their size, and their location. And a number of these are available now, both in the report and on the website. In particular, this shows a cross-section across the body at Descartes. This is the topography, and this cross-section in here shows the 3 different models from the geophysical inversion. And I invite you all now, there's also a QR code here, which will allow you to actually look at the 3-dimensional model. With an Android or iPhone device, for example, if you take a picture of that QR code, and I'll give you a minute to do that, it will send you to a web page that has that 3-dimensional model, which you can rotate and zoom in and out of. And there's a total of 24 of these models that are hosted on the website and are available for you to look at based on the 24 QR codes that are present in the report, which was released today. I'm going to assume that sorry, my window is blocking stop share. I'm just going to jump to a web browser here now, just to show you what hopefully you were able to pull up while I gave you time to scan that QR code. This is what should come up if you used your camera to capture that QR code. So basically you can take this, you can look at the surface of the body, but you can also basically rotate around and look at the three-dimensional model and where the location of the serpentinized ultramafic rocks are within this system. So again, there's a total of 24 of these available in the report. Now, one of the challenges we've had in this, this is a preliminary report. We're continuing to refine these geophysical inversions. And one of the areas that's remained a challenge for us is that the geophysical inversions tend to push the bodies to depth, whereas we know that these bodies are often outcropping. So right now we're getting results which tend, although we have done our best to push them to the surface, but there's some additional work that needs to be done to refine the geophysical inversion models. We feel that they're doing a good job of capturing the size of the bodies, but they have a tendency, because of the nature of the relatively coarse gridded regional data, there's a tendency to push the bodies a little bit to depth. So we're probably overestimating the material that's present at depth and underestimating the volume of these bodies that's present in the shallow subsurface, but we feel we are doing a good job at rendering the total volume of these bodies. We just have to work a little bit on their placement with respect to depth. So if we look at, so we've done this not for all bodies yet. We're about a third of the way through. We've done most of the major bodies in British Columbia. Again, the full report, the full results of this project will be released early in the new year. But based on the inversions that we've done to date, which are listed here for 8 different areas, we can look at here they're coded to their ultramafic locality, which are the boxes within this map. So you can see where they are in BC. We have the aerial extent of those bodies, where they're sort of A, B, or C classified ultramafic bodies. And so that gives us an area of about 2,900 square kilometers. And if we just assumed that they were on average half a kilometer thick, that would give us a volume of roughly 1,400 cubic kilometers of serpentinized rocks. But since we've done the inversions, we can actually do this with a bit more finesse. So if we just take the top half kilometer we get, of the imaged rock bodies within those same areas, we get a much smaller volume of rock. And we know this is in part because there's a tendency to be pushing the bodies to depth. So if we instead pick a cutoff of 1 kilometer, we get about 1,000 cubic kilometers of heavily serpentinized rocks within the ultramafic rock bodies in BC. And if we go to, and we can see though that the bulk of these bodies are actually, the largest amounts of the volumes are present at much greater depth within the existing inversions. We believe that this is partly an error because the bodies are being pushed to depth, and we're working to refine these models to do a better job of presenting the distribution of the bodies with respect to their depth. This is important because if we're going to use the rock bodies for carbon sequestration, then there's 2 main modes that we would use. If we're going to look at ex situ carbon mineralization, we would be counting on, we would be trying to capture CO2 from air within mine tailings, which means we would restrict our attention to the labile magnesium fraction of these tailings, and we would restrict our interest to the portions of these bodies that are present in the near subsurface. And for our purposes today, we've chosen the top kilometer. We expect that as our geophysical models are further refined, that these numbers will go up. This ex situ carbon mineralization process is the one that we already know happens at the Mount Keith mine, that we're demonstrating in field pilots, and that we know it can be implemented at relatively modest cost. So this represents maybe a smaller prize, but it's something that's technically feasible today if we design our mines to do this and if we focus our activities on the right mines. There is an alternative method for using ultramafic rocks to store CO2, and that's one in which the carbon dioxide is injected into the subsurface. This relies on the higher temperatures and pressures under those conditions to react all of the magnesium, so it represents a much bigger prize in terms of the carbon sequestration capacity, but it also represents a process that has not been demonstrated technically at any scale in terms of actual injection. So this is more of a long-term goal for carbon sequestration that's not currently technically feasible, nor would it be affordable, certainly at today's carbon tax. Nonetheless, we can look at both of these within the context of the ultramafic occurrences in BC. So the thing to keep in mind is we can think about the total magnesium content of these rocks or of the tailings that come from them. If we want to do ex situ, if we want to use tailings to capture CO2 from the atmosphere, we restrict our attention to the component of the magnesium that's labile, whereas if we're going to in the long term inject in the subsurface, we have the potential of accessing all of that magnesium. So we need to convert the volumes of serpentinized rocks that we have for BC into a amount of labile magnesium. And to do that, we've taken the one locality in the world that we've characterized in detail in terms of labile magnesium content is the Baptiste deposit within the Dakar Nickel District in central British Columbia. And this histogram represents a distribution of labile magnesium across roughly 1 billion tons of that deposit. And so what we did was take the average labile magnesium that's been determined from the Baptiste deposit, and if we assume that that applies to all of the serpentinized rocks in BC, we can start to get an idea of the sequestration capacity. So that's shown here for ex situ carbon mineralization. If we restrict our attention to the top kilometer, which we believe is an underestimate because the geophysical models are pushing the bodies low, that gives us a capacity of 56 gigatons of CO2. That represents roughly 800 years of BC's emissions at current rates. If we accept that those bodies are pushed perhaps a little deep and we look to depths of 2 kilometers, that number is roughly 4 times greater. Alternatively, the bulk of these bodies are pushed to depth, and in situ carbon mineralization, we can access all of the magnesium, not just the labile magnesium. And so in that case, we can do thousands of gigatons of CO2, but this is a technology which is neither currently demonstrated nor do we know if it's affordable. And this plot on the left is just to emphasize that these numbers come from looking at a number of localities around the province. There's 21 of these sets of models that are all present in the report, and each of them can be examined in 3 dimensions by scanning the QR codes listed here. Again, we've taken essentially the 21 largest bodies and then extrapolated them to the province as a whole, assuming that the other bodies behave proportionally. For the final report on this project, we will have completed the geophysical inversions of all those bodies, and so we'll have final up-to-date numbers in those cases. So to finish then, I just want to emphasize so it is important to emphasize this represents a substantial capacity to store CO2 within ultramafic rocks in British Columbia. Again, 800 years worth of BC's emissions. Of course, we're not advocating that we would mine 1,000 cubic kilometers of ultramafic rock in British Columbia. Rather, we've chosen a small proportion of the total ultramafic rocks in BC, and we're in a position to look at both their location and to rank them in terms of prospectivity for CO2 reactivity, so that these occurrences can then be compared against other opportunities, point sources of CO2, the presence of nickel and other commodities, to try and look at where are the best opportunities to try and develop this technology within British Columbia. This is a graphic kind of show how we would see ex situ carbon mineralization would be implemented. We have an understanding of the location of high labile magnesium contents within an ore body, and then we would essentially, as that material is extracted and crushed and then put into the tailings facility, we could essentially see 2 types of carbon sequestration activity. We would put more reactive material on the beaches and potentially circulate concentrated CO2, either captured from air or from flue sources or from flue gas, into those materials. But we also have the opportunity for direct air capture happening within the beaches away from this material as well. But if we know where this material with high labile magnesium is, we can actually deposit it differently within the tailings storage facility to realize maximum amounts of carbon sequestration. At the Baptiste deposit, we've done that exercise, and it's based on the 3-dimensional model we have for the distribution of labile magnesium within that deposit. We have estimated that if 30% of the tailings were reacted for its labile magnesium content over the life of the mine would be greenhouse gas neutral. And if more than 30% were reacted, the mine would be net negative in terms of greenhouse gases, i.e. it could contribute towards carbon removal. And this is important because, especially in the context of nickel, because of course nickel is a commodity that seemed to be showing a lot of potential growth because of the demand for nickel for the electric, for batteries for electric cars. So this represents an opportunity to develop resources in BC in a responsible way that could reduce the carbon footprint or supply chain of transformation of our transportation industry to electric cars, or potentially even be net negative in terms of carbon. And we believe that there's a great opportunity to develop this resource and this approach within British Columbia. So to summarize the results, serpentinized ultramafic rocks can be highly reactive to CO2 in air at ambient conditions. This creates an opportunity to use mine tailings to capture and store CO2, reducing or eliminating the greenhouse gas emissions of mine operations. The amount of CO2 storage is governed by labile magnesium content, which is controlled by mineralogy, and key changes in mineral content can be tracked with physical properties, which allows us to use geophysical surveys as proxies for carbon storage prospectivity. Comprehensive physical properties model based on BC occurrences of ophiolitic rocks is complete, and it's underway for intrusive ultramafics. Roughly 20% of the rocks in our database come from intrusive ultramafic systems, and roughly 80% from ophiolitic rocks. The BC ultramafic occurrences are ranked based on their geophysical response, and 46% of the mapped ultramafic bodies have significant zones of serpentinization. Inverse modeling offers insights into the size, geometry, and location, but we still have some challenges with those inversions. And preliminary conservative estimate is that shallow serpentinite bodies in BC have a labile magnesium content sufficient to sequester 56 gigatons of CO2, or 800 years of BC emissions. I'll finish by talking a little bit about where we're going next. Again, we talked about we're going to continue to refine the geophysical inversions to try and do a better job of bringing these bodies closer to the surface. We know from some sites, we have existing drill data and surface outcrops demonstrating that these bodies are exposed at the surface. We want to do a better job of reconciling the geophysical inversions with that geologic knowledge. We will be producing an atlas that not only looks at the geologic or the polygon occurrences of the ultramafic rocks in the context of their geophysical response, but we'll also be putting them in the context of the geology and min-file occurrences and other things. So a final outcome of this project will be an atlas for all the major sites in BC, so that this information will be readily at hand. And of course, because it's all linked to a prospectivity map, it's all going to be within a geographic framework, which will allow opportunities for resource development to be identified. With that, I'll open it up for questions.
Wow, thank you, Greg. That was quite the presentation and so much information in there, and great to see so many participants as well. We've been hovering around 100 people, and just looking through the list, so many people that are active in the industry and experts that have worked on these projects over the years. And so just a reminder to everybody that I see some questions starting to come in. If you have any questions, just drop them into the Q&A box down at the bottom of your screen. Greg, the first question to come in came from Thomas Bissig, and they're rolling in fast now, but Thomas was asking, presumably you're not looking at mining ultramafic rocks just for carbon dioxide capture. How many of those bodies would be likely to be related to nickel and other resources?
Yeah, that's a great question. And we know that some are, because we're working with industry partners such as FPX and Gigametals, where we know there's a substantial reactivity and a substantial resource. But we haven't actually overlain all of the information that we've gained so far across the min-file occurrences. So that's something we'll be teasing out for the final report, which will be released in the new year. In the long term, we might actually mine ultramafic rocks for their CO2 capture. If we can find bodies that have large amounts of rocks with particularly high labile magnesium, our calculations would suggest if the carbon tax was around $100 per ton, which you could easily get to, you might actually be able to pay for the cost of mining out of the revenues of the carbon tax, and have basically have those mines contribute towards global carbon removal. So that might be a long-term potential outcome, but in the short term, we're looking to decarbonize the electric decarbonize resource development and contribute towards low carbon battery technology, amongst other things.
Great. And so the next question that came in was asking what's needed to advance this technology in BC to sequester significant amounts of CO2, and is 30% of labile magnesium a reality?
Yeah, I believe it is. To put that in context, at Mount Keith, what's happening there by accident and initially unknowingly would be about 10% of, they're reacting about 10 to 15% of their labile magnesium. So you're talking about doubling or tripling what's already happening by accident. If you look at the Mount Keith nickel mine, for example, that's a mine in Western Australia. We know that our field trials have looked at both flue gas capture. At the Gaucho Gray Diamond mine, we flowed CO2, concentrated CO2 representing flue gas. So about 10% CO2 was flowed through a 250 kilograms of tailings last summer, and for 44 hours, no CO2 leaked out the tail end of that reactor. So we know that we can capture and store carbon dioxide from flue gas in mineral form in real time. That experiment flowed at about 1 liter per minute. It was scaled to roughly match the idea of putting all of their diesel flue gas into the full size of their tailings storage facility. And we've shown for 2.5 months now through the field pilot, using Baptiste tailings, that we can accelerate the capture of CO2 from air by a factor of about 3, and we can sustain that for several months through some of the surface treatments that we're looking at using that would apply to beaches, for example, in mine tailings, and we're working with companies to develop technologies which would allow those surface treatments to happen autonomously with rovers, so that we don't have to have people walking on tailings in order to optimize the CO2 uptake. So I believe that's very, very readily achievable with existing processes and existing technology.
So I'm going to skip one question really quickly here to get to the next one, which is related, asking what the typical fractions of ultramafic bodies that are serpentinized. So I'm guessing the question here is naturally what's already, what already might be serpentinized.
Yeah, so it's highly variable, I think. So to put it in perspective, if you look at the, so again, we said, 46% of the rock bodies in BC have large geophysical responses, but part of that reflects very small rock bodies. But if you look at the aerial extent of the mapped ultramafic outcrops, the aerial extent that has a strong geophysical response is roughly 75% of that. So that would argue that, the majority of the rocks are significantly serpentinized, but not significantly carbonate altered. And we don't need full serpentinization for this to happen. Some of the best rocks are actually partially serpentinized. And as anyone who's worked on ultramafic rocks knows, it's usually a frustration to the igneous petrologists that they have to deal with all this serpentinization, ruining their nice fresh igneous rocks when they're trying to study igneous processes. So it is fairly prevalent, but we don't need full serpentinization in order for the rock to be reactive.
Okay, and yeah, the questions flying in, and great to see some really kind of practical questions in terms of like what do we do with this? How do we take this next? So a great question here, I think, from Ron Monk. Can you discuss how CO2 capture can be measured and verified so it can be considered in mine GHG reporting in the province? And also, can you discuss the potential to monetize the value of CO2 capture? I'm sure something that you've been thinking about yourself, Greg.
Yeah, in our early work was all really geochemically focused. So we used 3-isotope system to track sources of CO2, and we used mineralogical analysis to understand how much CO2 was trapped. We've augmented that with stealing technology from soil science and from atmospheric science. So I'll just throw this back up quickly. This is a field pilot that we ran in Atlin this summer. So this shows an array of dynamic closed chamber soil gas systems here. We were measuring continuously for a month the flux of CO2 in and out of the alkaline flats at the town of Atlin. We chose these because they're kind of tailings-like in that there's not a lot of vegetation and you have a lot of desiccation cracks and other things that are going to be challenges for this technology. In this particular case, the CO2 that's forming, these are all carbonate minerals that you're seeing, and they're actually coming from a deep source, geologic source of CO2. So this is a site of CO2 emission, not a source of CO2 uptake, but it's in mineralogically similar materials and physically similar materials. So we've been, since we were blocked out of going overseas to test some of this technology in some large mine sites in the Southern Hemisphere, we've been testing them in sites in BC. So we see a very good correspondence between geochemical and mineralogical monitoring techniques and techniques that are well established for carbon sequestration from agriculture and forestry, including both dynamic closed chambers. And also this year, we did our first pilots with eddy covariance towers, where we can essentially correlate CO2 concentration with the vertical component of atmospheric eddies in order to understand the CO2 flux in and out of landscapes. And both of those show promise. They will have a lot of value. They're both already well established as technologies used to track carbon fluxes in agriculture and in forestry. So we are optimistic that these approaches, once they've been validated for mine tailings work, would be readily adopted by the community. And in terms of monetization with the verification protocol, basically, well, right now there are huge private markets. You just have to think about announcement by companies like Microsoft and Apple and Shopify. There's already incredible private markets that are trading carbon credits like this currently, and with some policies in place, we're very confident that these things will fit within legislated which fit within jurisdictions such as British Columbia and other places around the world where there's a carbon tax to also allow monetization under that framework.
So that fits really neatly with another question which has popped up, which is relating to the fact that you've done some economic analysis around this, and asking if you have a sense at the moment of whether there's a floor carbon price that would be required to justify using this kind of technology.
Well, if you look at Mount Keith, they're doing 40,000 tons a year by accident. So they have a cost of $0 per ton to do 40,000 tons. Microsoft would jump at the opportunity to buy 40,000 tons of carbon mineralization today, and it's effectively free in that instance. Of course, you couldn't sell that because you didn't do it intentionally. So I think there's, as the floor price goes up, the amount of carbon goes up, but there are opportunities right at the bottom end of that. But in the context of 45Q and the low carbon fuel standard in California right now, people, a floor price of $100 to $200 US per ton is pretty common in some of these private markets for carbon sequestration of the value of mineralized CO2, in which there's very, very low long-term release risk. The cheaper carbon tends to be things like soil carbon and forestry carbon, where forest fire or a change in agricultural practices can erase activity in relatively short, erase past carbon uptake in relatively short order. So this type of carbon sequestration has higher value, and the current prices that are being, the current markets are operating at a scale where this is already viable, I would argue. We need more pilot projects to scale this up quickly.
Okay. So sorry, my questions are bouncing around. So an interesting question that's come in here, saying thank you for a great presentation. Are there any potential uses for the tailings that have high labile magnesium concentrations, like concrete or other products?
Yeah, we see co-benefits. We can get some very strong cementation. We have a Sterling Vandersea has a Geoscience BC paper from a couple of years ago showing some of the strengths that we can get from unconfined triaxial compression tests. So you can get co-benefits within the tailings pile in terms of stabilization. Sasha Wilson at the University of Alberta has shown that you can probably actually pull up some of the toxic metals within the carbonate minerals. So you may actually be immobilizing toxic elements, and we can anticipate that we can help reduce dust if we're cementing these materials. So there's co-benefits within the tailings pile. There are companies such as Mineral Carbonation International out of Australia that are seeking to turn these things into building products, and that's another viable technology. One of the challenges in the mine tailings environment, though, is typically the large volumes of appropriate materials aren't necessarily located near markets that would allow you to do those kinds of pairings very cost effectively. Speaks to why there's so few brick buildings in Vancouver, because we don't have any clay nearby. Hard to move rocks or geologic materials economically. Okay,
great. And then I'm going to just pull together a couple of questions because I think they're related. So one of the questions was in the video that you showed, the humidity increased significantly. So you were able to say what the reaction going on was, and was water a byproduct? But I'm going to link that together with another question also, which came in, which was what happens with some of the other things you see commonly with these emissions, like methane, during these reactions?
No, great questions. In that particular example, the reason the humidity goes up is that the tailings are moist, and so they're evaporating into the room air. And so once we isolate a fraction of that room air against the tailings, the relative humidity goes up in that environment. Water content is critically important. If these tailings buried underwater react very slowly because the gas can't get in there. So typically what's rate limiting in the first instance in these things is CO2 transport. So for that, we need gas diffusion down into the pore space of the tailings. And so high water saturation blocks that. At the same time, these reactions are mediated by water, and so water needs to be present. We're reacting hydrous minerals such as serpentine and brucite, which is magnesium hydroxide, but the minerals we're forming are magnesium carbonates that are also hydrated. So these reactions in some cases actually consume water, not release it. There's no significant methane production associated with these reactions that we have seen in the lab. We have not, systematically tested in the field environment, but the methane production associated with ultramafic rocks is typically associated with the serpentinization process. And in this case, we're actually consuming the serpentinite rocks, not producing them. So there's not really a pathway there for methane, but expanding our analytical portfolio to include other greenhouse gases is one of the things that we're currently working on. It is a bigger concern in systems with a lot of biological activity, because you can start to bring in other pathways with methanogens and things like that that might actually be potentially a greater source of concern in that instance. So I think the soil carbon in places like that, soil amendment, which is an interesting research space, have to be careful about methane production in those instances when you could get a lot of reduction associated with microbial activity. It's not a lot of, in these systems abiotically, there's not a good pathway for reduction associated with carbonation.
Okay, so there's another great question here, which gives you a good excuse to talk about some of the other research that you're doing, because I know that the part of the research that's funded by Geoscience BC and that we're focusing on here today is just one of a series of projects. But so the question that came up was if there are any plans for in situ sequestration tests. But like I say, I guess that gives you perhaps a good excuse to talk about some of the other projects that are going on alongside this one.
Yeah, that's a fascinating area of research. There are a number of groups internationally in that space, and the area where there's been the largest demonstration projects and success have been in basalts, not in ultramafic rocks. And the Carbfix project in Iceland comes to mind for that. There's also a very successful injection of supercritical CO2 into the Columbia River basalts, where they see mineralization happening in those systems. They're targeting the tops of lava flows that are kind of rubbly and have porosity and injectivity. Within ultramafic rocks, Peter Kellerman is out of Columbia University, is the main proponent for injection into ultramafic rocks, and for the fast reaction that he's targeting, there's a sort of a sweet spot in terms of temperature pressure space, which for the geothermal grading around here would correspond to depths of in excess of 2 kilometers. So this idea of whether or not these bodies extend to depths of 2 kilometers, which many of the geologists that have mapped them would question, although there aren't really firm data. The whole idea of whether these inversions are pushing things too deep is really important for the in situ approach, because if the bodies don't go deep enough, you don't get into the temperature pressure sweet spot. And you don't know till you drill that first hole, so it could be a pretty expensive mistake. So we certainly, one of the things we will address in the final report is further ideas on how we can we find those areas in BC that might have deeper ultramafic rocks. And gravity surveys come to mind as something that probably are going to be a lot more sensitive. There's very little gravity data that we've been able to use so far, but you may have noticed, some of you may have noticed in the slide deck that there's strong changes in density associated with these reactions. So we could use gravity for that. South of the border, especially to California, there are well-known very thick sequences of ultramafic rocks, as well as in other places like Norway, and I think those are localities where the people that are looking to first to test CO2 injection into the subsurface are I think focusing on places like that more so than BC at the moment.
So a two-part question next. So asking, do you think the current measurement technology is, so that the quantification is ready for any of BC's GHG gas reporting facilities to launch pilot projects? Or could you estimate the cost of such projects? Maybe that second bit is a little difficult, but
I'm not sure. So in terms of using existing, we don't have any operating ultramafic mines in BC. So to looking at ex situ mineralization, we would be looking either at using existing stockpiles of tailings or something associated with an operating mine. You know, I think the easiest pathway towards low cost and easy adoption is to design around this. So it's much easier to design for this and do it at low cost than it is to try and bolt it onto existing facilities. That being said, there is potential to certainly take old stockpiled ultramafic tailings and potentially use them for carbon capture. We've done baseline studies at Cassiar many years ago now, Clinton Creek in the Yukon and other places. So the historical asbestos mining in BC and the Yukon would be some of the areas of historical resource development where there are legacy tailings piles. Not much is happening at Cassiar because it's frozen in the core, so nothing's getting in down deep, is what we found when we first studied that in about 2005.
Great, thank you. So yeah, we're getting towards 11 o'clock, so I think we'll make this the last question. I apologize to the questions that we don't get to, but I hope we'll have other opportunities to talk about this. An interesting question, have you done any work around in situ carbonation of basalt following the injection of CO2 rich fluid?
Yeah, we haven't worked in basalt ourselves, but there is actually a fairly significant research community working on that. There's also a project sponsored by the Pacific Institute of Climate Solutions that's looking at an offshore injection of CO2 into Juan de Fuca area, offshore BC, potentially coupled with direct air capture system, sort of again long term. So you know, the area where there's been the most success is the CarbFix project in Iceland, where they are taking the CO2 that is released with the processing of geothermal fluids and redissolving that back into the re-injection fluid and pushing it back into the reservoir, the geothermal reservoir. And they've demonstrated that over, it's about I think about a kilometer path length between the injection and the wells where they're extracting the hot water again. They're demonstrating that the CO2 is mineralizing over those distances within the existing hydrothermal system. So that's very promising. It's not a scenario that's easily translatable to a lot of other places, but there have been injection tests, again, in the Columbia River basalts that supercritical CO2 that yielded evidence of mineralizing CO2 within those reservoirs in relatively short order. What we don't know is how sustainable that is. Are they accessing small amounts of highly reactive minerals such that these initial small tests are achieving mineralization? Do we know if that applies to the bulk of the rock? I think of those systems as kind of being like the way we look at labile magnesium and tailings, that you know, the bulk of those basalts are not going to be the sequestration capacity of those basalts. The bulk of it is probably not going to be fast reacting. So you need to understand and target the reservoirs within those systems where there's a high fraction of reactable material versus a lot of the bulk minerals, which will react over much longer timescales. Not really expecting the pyroxenes to react very quickly under those circumstances, for example. Not sure if that was an answer, but
thank you, Greg, and yeah, on behalf of everybody that's been listening, thank you for today, and I'm looking forward to the final report being ready early next year. Before we leave, just a couple of quick points and quick reminders for folks. I'm just going to share my screen very quickly. I hope very quickly, if it's going to behave. There we go. I know there's been a lot of interest in this project, and a reminder that there's lots of other projects going on with Geoscience BC too. So we'd encourage everybody listening to sign up for Geoscience BC's regular email updates. So if you go to our website, which is geosciencebc.com, scroll straight to the bottom of the page, and you'll see a subscribe for updates button there. That will make sure that you get any upcoming updates on this project, but also on the many other 40 or so other active projects that we have going on at the moment. And on the subject of staying up to date, a reminder for everybody that AME's remote roundup is coming up in January, from January the 18th to the 22nd. Registration is open, and I understand that the early bird discount ends on November the 20th. Geoscience BC, this is always a big event for us at Geoscience BC. We always have some exciting updates available at Roundup. And for 2021, we'll also have our summary of activities volumes from 2020. So those give you summary papers for the vast majority of the projects that we've had going on through the year. So a great opportunity to catch up on all of the research that's coming up. And then finally, before we leave, just a note to keep an eye on your email over the next couple of days. We'll email you links to the YouTube version of this webinar, and also a PDF of Greg's presentation from today. And so there we are. I think we're finished. Again, thank you, Greg. That was a great presentation. Great to see so much interest, and hope everybody has a good day and a safe week. Thank you, everyone.